Hello everyone, my name is Rebecca Jancourt, and today my team and I will be presenting our solution for a municipal wastewater treatment facility in Huayba, Guatemala. We'll begin by explaining the background of this project, including how it came to be and our client's needs. Then we'll analyze 3 alternative treatment systems, and finally we'll provide our recommendation for the community. Our project team consisted of 4 environmental engineering students. Christine Bolen-Prom, Jamie Wynn, and Jamie Sikora have since graduated from the Milwaukee School of Engineering with a bachelor's in civil engineering, specializing in environmental engineering and water resources. I will be pursuing my master's degree in the same field. Additionally, construction management students Blake Bostwick and Julian Son served as CMs on the project and have since graduated as well. This project came to be when Christine visited Guatemala in spring of 2019 on an Engineers Without Borders trip. She met with the mayor of Huayba, who asked if MSOE students would be interested in completing 30% design of a decentralized wastewater treatment facility in his community. This project was part of a plan to implement wastewater treatment in Huayba. 5 sites have been selected to house decentralized wastewater treatment facilities. The systems for sites 1, 2, and 3 have been designed by a Chilean engineering firm and have already been constructed. Our team was tasked with designing a suitable wastewater treatment system for sites 4 or 5. We selected Site 5, which will serve a population of roughly 5,000 people within the community. As you can see, Site 5 is located south of central Huayba. This site was chosen because of its proximity to Rio El Arco, the river south of the site. This configuration will allow for the treated water to be discharged directly to the river. Additionally, the slope of this site is approximately 20%, which will allow most of the system to be gravity fed. The site consists of several parcels. The municipality of Huayba owns 1,200 square meters of land located directly north of the river. Adjacent to this parcel is 600 square meters of private land. Furthermore, the land south of the road is public right-of-way. Both of these parcels will need to be acquired prior to construction. The total area, assuming successful land acquisition, is 2,700. Taking our client's needs into consideration, we developed 5 criteria for this project. The top criterion was reliability. We define reliability as the likelihood that the system will fail if upkeep is not properly maintained. The goal of this project is to provide the community with sanitized wastewater. If the system fails, we will be unable to achieve this goal. As previously mentioned, the area of the site is only 2,700 square meters. The treatment system must be able to fit on the site and accommodate for future growth. Because size is a limiting factor, land requirement and feasibility of the system was assigned a weight of 25%. The area around the selected site experiences frequent power outages. Because of the unreliable energy supply, the client requested a system that has low energy consumption or one that could be powered on an alternative energy source. The community has few trained wastewater operators, so it is important that systems requiring little or simple maintenance are considered. Lastly, because of the high-valued equipment and materials that will be used in the system, it is important that safety and security be considered. This will not only protect against theft, but also protect the public from dangerous treatment processes. This criterion accounts for 10% of the project.
Based on the 5 criteria mentioned, we looked into 7 different secondary treatment processes as alternatives to meet the community's needs. After preliminary research, aerated lagoons, activated sludge, and anaerobic digestion processes require consistent energy usage and routine maintenance and attention to operate effectively, so they were not further analyzed. And while algae treatment was initially considered because of their off-grid operability, this process has intensive maintenance and significant land requirements that the community does not have. Rotating biological contactors were considered for this project because of their low energy requirements. This process can be designed to efficiently utilize space, which is ideal for this site with limited land. Trickling filters are fairly reliable and only require energy to distribute water over its medium. This process only requires daily observation to ensure that the system has proper ventilation and is not clogged. The last alternative considered is the subsurface constructed wetland. This process operates completely off-grid and does not require any mechanical components. The wetlands only need maintenance for its plants and pipes. This treatment process does require a large area of land, but its minimal energy consumption and need for maintenance were optimal features to consider for further analysis. Ultimately, the rotating biological contactor, trickling filter, and constructed wetland were further researched for their feasibility with the design criteria. These processes were also assessed to ensure that they can efficiently treat the high concentrations of BOD and TSS in the wastewater to meet the limit of 100 milligrams per liter of BOD and TSS, as stated in Guatemala's standards of Acuerdo 236. But with the expanding population of Hoiba growing at about 2%, the treatment processes would be designed to 50 milligrams per liter of BOD and TSS instead. Guatemala also has wet and dry seasons that significantly affect the flow rates, where the max flow rate is about 90 gallons per day per person and the average flow rate is about 30 gallons per day per person. The first secondary treatment process we looked into further was the rotating biological contactor, or RBC for short. Some advantages into using the RBC is that they're built as rectangular units to save space, which is ideal for the limited land available. When we were speaking to a Evoqua vendor representative, they recommended a unit with a size of 8 by 4.5 meters to meet with Hoiba's effluent needs, and this fits right into the site. Maintenance tasks are relatively simple. It requires regular weekly, monthly, and annual maintenance and inspection for its mechanical parts to ensure optimal performance. It also has low energy consumption to run the motors to rotate the discs. Some disadvantages, though, into using the RBC is that it takes time to train an operator to learn the proper skills to maintain the system. If not maintained properly, the system can easily fail. They're susceptible to shaft failure, so operators will need to make sure that mechanical components are maintained and that there isn't too much buildup of bacteria on the disc. Because of this, it's fairly unreliable. The motors must also continuously run to prevent microbial deterioration and failure of the system, which might not be possible due to the frequent power outages. The components within RBC are also at risk of being stolen, so the system will need to be covered in a protective building. The second treatment process we further researched was the trickling filter. Some advantages into using the trickling filter is that it can utilize locally sourced materials, such as rocks, so they would not have to worry about shipping and transportation and storage available parts. It could also potentially take advantage of the site's steep slope for its hydraulic head to distribute wastewater and allow for easy construction integration onto the site. It also has simple maintenance tasks to ensure that the media is not overgrown and clogging the system. Even if the trickling filter is clogged, the system will still work, just inefficiently rather than failing. Some disadvantages, though, into using the trickling filter is that if the media is clogged, it can create surface bonding and cause uneven flow distribution, develop harsh odors, and attract vectors such as flies and mosquitoes. It also requires energy for recirculation pumps. The third treatment process we considered was a subsurface constructed wetland. Some advantages of using the wetland is that it's reliable as it operates on its own without operator interference. It does not utilize energy as the stones and plants in the wetland treat the wastewater as it flows through the system. It has simple maintenance tasks such as unclogging the inlet and outlet pipes, replacing any damaged plants, and routine checks of the wetland conditions and effluent concentrations. These tasks are easy to learn and could be taught to any operator quickly. However, there are two large disadvantages that outweigh the advantages. To meet the 20-year design population, a wetland of nearly 88,000 square meters would need to be constructed, which is unfeasible because the available site size is only 1,200 square meters. Even if the available site was large enough, a 20% slope would require extensive excavation to achieve the 1 to 2% slope for the wetland to operate properly. After analyzing the advantages and disadvantages of the three alternatives, it was determined that the RBC was the least ideal treatment process for the community of Hoiba. This process has a high risk of failure and overall does not score well with the criteria to fit the needs of the community. While the wetland scored high with most of its criteria, its land requirement was too unfeasible in comparison to the available site size. Ultimately, the trickling filter was the best treatment process for the community of Hoiba. The process has a low energy consumption, simple maintenance tasks, and is fairly reliable even when not properly maintained.
Looking at the overall process flow diagram, the process starts with screens, followed by a joint primary clarifier and equalization basin. The secondary treatment recommended is a trickling filter, followed by a secondary clarifier with recirculation. Future contingencies for chlorination are also accounted for. The detailed site plan and hydraulic profile can be found in our report. Screens will be comprised of 15 bars and will be manually cleaned by an operator. The screens include a bypass channel in the event that bars become clogged. This is a fail-safe design to account for any missed maintenance. The primary clarifier serves three purposes: settling out solids from incoming wastewater, equalizing flow, and distributing wastewater to the trickling filter. The design of the system was based on the typical overflow rates for the primary sedimentation that is followed by secondary treatment. These values were taken from a wastewater engineering treatment and resource recovery by Metcalf and Eddy. The required size is 21 square meters based on peak flow. For the hydraulic retention time of 2 hours, it was determined that a height of 3 meters would be required for the tank. 1 meter of height was added to ensure room for the sludge storage, and because the tank also serves as an equalization basin, an additional 1 meter of height was added. The primary clarifier features a 2.5 meter steel inlet baffle to distribute the flow of incoming wastewater. Solids will settle in the bottom of the tank and flow via gravity to the sludge drying bed. The 6-inch diameter pipe has a butterfly valve that will allow the operator to control the flow of the sludge. There is an outlet baffle to skim the surface of the water and collect scum. Scum will be removed from the surface of the water manually by an operator using a skimmer and collected in a box on the side of the tank to await disposal. Following the outlet baffle is an outlet weir which flows to the distribution portion of the tank. There is an inlet from the secondary clarifier that recirculates water to the distribution portion. This is also an 8-inch diameter overflow pipe that directs water to the chlorination tank prior to discharge in the event of excess flow. 4 4-inch diameter pipes distribute the water to the trickling filter. Each pipe has a butterfly valve that allows the operator to manually control the flow to various cells. Effluent from the primary clarifier will flow to the secondary treatment processes, beginning with the trickling filter. It is important to us that we design a modular system that will not only service the population in 20 years, but the current population. For this reason, the current year, 10-year, and 20-year population was analyzed. According to 10 state standards, a trickling filter must be designed to accommodate peak weekly flow rates. The trickling filter was designed using two methods: hydraulic loading rate and organic loading rate. The acceptable ranges are given by Metcalf and Eddy and can be found in the appendix of our report. The hydraulic loading rate yielded a surface area of 420 square meters. This fits within the acceptable range of organic loading rate. The system will be comprised of 4 separate treatment cells to accommodate the growth of the community. These separate cells will have the ability to be individually taken out of service for maintenance. The media will be locally sourced rocks. Each treatment cell will have 5 separate header pipes to evenly distribute flow. The pipes will be supported by the wall at each end and by a pier in the center. The pier also serves as a footing for the trickling filter. Since we are not using forced ventilation, the air passage to the underdrain will be critical. The underdrain catchment system that holds the rocks will be cast-in-place concrete with holes. This design was utilized at another constructed wastewater site in the community. The underdrain will be sloped at 2% parallel to the slope, where it will then flow into a channel that is open to the environment, sloped at 2% towards the middle, towards the effluent pipe. It will also have platforms over the end to allow the operator to inspect the filtration of the system. 2 observation ports will be utilized so the operator has the ability to look down into the filter and make sure that the water is able to trickle throughout the entire system. If there are any clogs in the system, the operator will be able to identify at which depth it is happening and if it is within the trickling filter or within the underdrain system.
Following the trickling filter, water will flow into a secondary clarifier to settle any solids produced from the trickling filter. This is designed similar to the primary clarifier that was mentioned before. Size is based on the larger value between the average flow and the peak hourly flow using typical surface overflow rates found in Metcalf and Eddy. From the design criteria, it was determined that the clarifier should be used for a peak hourly flow and should have a surface area of at least 57.5 square meters. It was also designed to have a hydraulic retention time of at least 2 hours. With those mentioned values, the resulting clarifier looks like this.
To help utilize the small site area, it was determined that a rectangular clarifier would be more preferable over a circular clarifier. A sloped bed allows sludge to settle by gravity and then be gravity fed to its respective sludge drying bed cells. An overflow weir placed near the discharge end of the clarifier is used to help control the level of water in the tank. This should also help with the removal of any floating contaminants in the clarifier. However, since the trickling filter does not produce much scum, this is not a huge concern. The discharge pipe leads to a recirculation box. This box is essentially a wet well where the effluent can be gravity fed to the chlorine tanks or pumped back to the distribution box of the primary clarifier. This recirculation box was sized based on the size of a submersible pump needed for an average flow rate of 9.7 liters per second and a head of 6 meters. For tertiary treatment, we designed a chlorination process utilizing a chlorine tablet injector and a contact basin. The contact basin was designed per 10 state standards using a peak hour flow, a peaking factor of 3.1, which led to a design flow of 30.1 liters per second. This will accommodate for a 15-minute contact time and the recommended constant water depth of 2 meters. Water will first flow to this highlighted box. Here, chlorine will be injected via tablets from a tablet injector. This injector will have a flow control weir inside, meaning dosage will be controlled by the rate of flow in the device. No moving or electrical parts needed. This is an extremely common application in the area, using calcium hypochlorite tablets at a 70% concentration. Water will then continue to flow through the contact basin to be mixed. Sludge from the primary and secondary clarifiers will be dewatered on sludge drying beds. Sizing of the bed is based on sludge production, as well as the design of drying beds on other sites in the area. The primary clarifier produces 1.56 cubic meters per day of sludge, and the secondary clarifier produces 1.66 cubic meters per day. The sludge will be applied in a 250 milliliter thick layer and allowed to dry for 10 days. The design of the bed features 4 cells, 2 dynamic and 2 static. This design allows sludge to continue to flow into the beds while dewatering is occurring. The underdrain of this bed will be composed of locally sourced sand and gravel. Currently, the construction of this bed is unfeasible due to the slope of the site. Therefore, we would need to meet with the client to understand how sludge handling will occur at the site and determine the best course of action. The dewatered primary sludge will be disposed of, while the secondary sludge will be moved to a compost bed to allow for agricultural usage. Lastly, we developed a cost estimation for NA materials and labor. These values are much lower than typically seen in the United States, which is primarily due to the lower labor wage. On average, workers receive wages that are equivalent to under $1 US. Following extensive site excavation, clearing and grubbing, slab-on-grade foundation and walls for each treatment process will be constructed using hand pours of concrete. Hand pours are typical in this area due to the lack of equipment. Altogether, this project is estimated to cost the community of Hoiba just over $16,000. This value was calculated using the typical labor rate and material costs in the area, first in Guatemalan quetzals and then converted to US dollars for a better understanding. Moving forward with this project, it is imperative that we keep a relationship with the community of Hoiba. Thankfully, some of our team members had traveled to the area before, so we were able to make assumptions regarding the soil on site. Obtaining actual soil samples and site data in the future would help immensely with structural design, which we assume to include pilings for stability. It is also important to note that with a limited site area, we were not able to implement all designed parts of the treatment process. The composting bed was designed to receive the total volume of sludge produced from the secondary clarifier sludge drying beds. It was then to be disposed of safely or reused for agriculture. We are also aware that we designed these processes to meet 10 state standard effluent limits, which are much lower than the standards outlined in Acuerdo 36. Resizing these processes would reduce the size of each system, allotting more space for every step to fit on the site. And that concludes our presentation. Thank you for your time. We look forward to any questions you may have.